microphones here, and I have a microphone there. I've never been so microphoned in my life, but so I will yell, and if you want me to yell more, you can just tell me. Yeah, this applies. So if you can't read the code up there, that's the worst case scenario, and I will explain also code. That's fine. So if you want to move forwards, maybe not that many seats, you can. That's fine. If you move around during the talk, that's okay also. That's fine. And if you like this idea, please steal it. You don't even have to credit me. All right? Cool. Sold. So I'm going to be annoying for like an hour and a half. I hope that's okay. So, kind of tricky to find a name for this kind of talk, because this is like, I'm going to try to give you as much information as I know. People are at different like programming levels. Some may be newer, some may be more like knowledgeable. So it's tricky to find out like where should I put the line. So it's miscellaneous things that I find neat about C++. If you all know them, I'm very sorry. If you don't, and this is too much for you, I'm also very sorry. Okay? We sold? Good. This is my face. This is my name. I'm a senior software developer at a company called Factlines. And if you type those names on most social platforms, I'm there. You can find me. And you can yell at me on the internet. That's also pretty cool. People do that. So if you want to do that, you can do that. I work for a company called Factlines. We deal with the exciting world of sustainability and supplier networks, and also EU taxonomy and law. So for you gaming people, this is probably very exciting. But hey, I went from gaming to this, so I mean, this is interesting, just differently. So maybe for some of you, who is this person on stage? This is a photo of me when I was younger. Mitch Hedberg joke, anybody? No? Okay. I worked in ATC systems, so air traffic control, programming air traffic control systems for about a year and a half. That's also a very interesting business, but for a completely different reason. I'm in the Keflavik Tower, if you've ever been to Keflavik. So we got to experience the tower and see all that kind of stuff. And like those classic movies, we had because there was an incident happening at the airport while we were there. So there were 2 US jets. They were doing a practice run, and one of them broke in some way, so they had to do an emergency landing. So there was like a helicopter flying over and doing all sorts of things. So after everything was landed and everybody was okay and safe, the helicopter did a buzz over the tower, which was kind of like one of those movie moments. And I'm like trying to find my phone, like trying to record, but no, too late. Too late. And yeah, I was in the gaming industry for 7 years. +1 for you if you can find me in that photo. I'm in that photo somewhere. This is the, so I was working for Ubisoft Massive. This is the release of the Division 1. So this is part of the team, and also like the other teams that were working on other games. I was more in the back end, like all the systems that make all the games work. So I usually say, I worked in gaming, I worked on all the games, and also worked on none of the games. Because I wasn't directly on a game, but I was basically for every game launch and all the backend systems and friends and invites and downloads and achievements and all this kind of stuff. A lot of server stuff. And I also do this once in a while. So I was a consultant in Norway, which is why I came here first. And I also do these kinds of talks. So I'm a professional yeller. I yell at people. So it's been a theme for the last couple of years for me to have like one of those, I don't know, hipster philosophy quotes in the beginning of all talks. So this is one of them. Before beginning a hunt, it's wise to ask someone what you're looking for before you can begin looking for it, right? So before you start your schooling, your education, you need to ask someone what you should be learning and knowing. And this is, of course, Winnie the Pooh. I recommend going looking for Winnie the Pooh quotes, because they're all philosophy quotes. This is all just, I'm certain that a Winnie the Pooh book is just a philosophy book for kids. So yeah. Okay, so ramble. Here's what's going to happen. I'm going to ramble about C++ for a while. So who here likes C++? Yeah? Who here is an expert at C++? Yeah. I don't think anybody is. I don't think Bjarne even is. I'm going to show you some features. And I'm going to show you, in my opinion, some best practices. I'm going to need something from you in return. I want you to listen, of course. I want you to take stuff in, like you do. And I also want you to ignore my advice. Yes, to a point. So I want you to be here. I want you to listen, to see all these things. And I also want you to say, yep, screw that guy, right? Because there is a reason for this. It's kind of a weird psychological reason for this thing. Because I want you to make mistakes. I want you to mess up. I kind of need you to make mistakes, right? Why? Which one of these do you think is more effective? I'm not going to do thing, which I'm going to do. Why? Because some dude at school told me not to. Some dude at school told me, this is not a good idea, right? Or, I'm not going to do thing. Why? Because I've been there. I saw it, I messed up, and now I have an emotional connection to this, right? How often have you talked to your classmates and been like, oh, I had this bug, let me tell you a story. And they go on a very emotional rant about that bug, right? And then the next time you spot the bug coming, you're typing away, you're doing something, you're writing something, and you're like, oh, wait, I've been down this road. It's a painful road, I shouldn't go there, right? So, in order to become a good programmer, you do this about 1,000 times for about 20 years, and then you're okay. Right? See? Okay? So, it's like, yeah, I can show you cool things. How many of you can remember all the cool things I show you, right? But when you make mistakes, then you'd be like, ah, I now have emotional connection. So this is why, like, yeah, we're going to have some fun. I'm going to show you some neat things. But, hey, I'm entertainment, right? I'm something to show you, right? I need you to make the mistakes. So, because you're in school, this is the place to make mistakes, right? Make them while you can. There's a second thing I need from you. I want you to be pragmatic. This might apply to only some of you, because some of you are like, oh, I want to be really nerdy about all of this tech stuff. I'm going to show you some stuff. If the stuff I show you is not a direct solution to your problems, please ignore, right? This also applies to when you continue learning and learn about this new cool feature in the language or some other language, right? If it's not a direct solution to your problem, please ignore. Because tech, yeah, is neat. I like tech. I like to be nerdy about tech stuff. Programming is neat. Guessing you know about this kind of stuff, range space for loops. The idea is, what is the generated code? It's nothing, because I have optimizations on. There you go. There you go. The idea with the tool originally was to ask the question, is this going to cause more code to run or less? Because this was a new feature in Cplusplus 11, I think. And he was working in a high-speed trading firm. And with a high-speed trading firm, you need to squeeze out every single byte and every single cycle. There's an interesting fun fact about like these high-speed trading companies, at least for some of them, because they need to do these analysis and make these decisions, and then once the correct decision has been made, they make the trade. And they do this like thousands of times a second. But that means that 999 times out of 1,000, they say no to the trade. And then one of the time, they say yes and make the trade. That means that the hot path of the code is the not trade. And the cold path, the stuff that's not in a cache, is, yep.
Does this fall in line with Big O notation?
No, it does not. Because Big O is about scaling. Like if you have data and then you're using, basically you have a list and then you have a list of lists and you're checking both of them for every item and then every other item. This is about, because when you're executing code, and we'll go more into this in a bit later, if you recently executed it, it's in the cache of the CPU. So the trade code is not recently in your cache because it's running so rarely. But that's the important one, right? That's the thing that should run as fast as possible. So for some of these firms, they always do the trade. But for some of the trades they want to say no to, they just don't send them over the network. So the code is always being executed, but the network traffic is being blocked, not the code traffic. So that's kind of these weird optimizations that people do. So they are very interested in, like, is this versus like a regular, like this one. Like this stuff. Is this better or worse? Am I adding more code to what I'm running, right? So the tool was originally made to go here and look at this loop and see like, oh, is this better? Is this adding more or less code? So here, in this gray part here, that's a part of the loop. We don't have to go into this. But if you want to look at assembly, this will also explain assembly to you. So if you mouse over here, it will tell you what it does. Very cool tool. You can pick from a compiler, many compilers, pull a bunch of options. So yeah, this is a wonderful tool. It will also optimize things for you. If I do like, I can show you a quick thing. So I make a vector. It's empty, has nothing in it, or I can just do it like this. And then I ask for the size. So if I compile this, I have a bunch of code, right? But if I optimize this, no code. Because the compiler figures out that, oh, you're not actually using any of this. And I know that this vector is empty, and you're asking for the size of it. So this XOR EAX is 0. That's what it does. XORing a number with itself gives nothing. So that's what it does. It gets quicker. So this is Compiler Explorer. This will be very useful. I will show you, we will go back to this. I will also show you a screenshot from this. So we'll see that. The other one is CPP Insights. You can just get from there from clicking here. This is another tool. Oops, accept, sure. The idea here with this tool is when you write code, a lot of the code that you're writing actually isn't the code that's then executed. So again, in this case, this is not the code that's actually being executed. This is the code that's being executed. But things like, if I go back to the const.x stuff, I have this loop over here, and I return stuff. If I run this, you see that this isn't the code that was actually made. Because this, a lot of this code here, isn't the thing that compiler compiles. First, it gets transformed into other code, and then that code gets compiled. So a range-based for loop is a regular for loop, but you get a begin and end iterator to the vector. And then that's the one you're actually executing. So usually what we call syntactic sugar. So this is convenience for this, because who wants to write this? Right? A lot of this is because it's like technically correct. So this like GNU CXX normal iterator, like it doesn't, a lot of this doesn't matter because it's just technically what's being outputted. But yeah, so this is what's interesting with this tool, and we'll see a bit of it later. Okay? Any questions so far? Any thoughts, comments, dad jokes? No? Cool.
Actually,
yep.
Since that range-based for loop compiled into that big block, is the range-based then less efficient than the normal one?
So the range one, if we go back to this and run this here, this is the same as if you would do auto begin is stuff.begin, and then I think it is for, don't do anything, if, no, you could do, it is begin if it is not equal to stuff.end, it ++, and then you would have to do something like this. So you're not using numbers or indexes to iterate through, you're using iterators. So I get the begin iterator from the vector, and then I use that as the first one. I think I do this. And I say, as long as I'm not at the end iterator, make the iterator go forwards, right? That's what this one here is doing. You can see there's a begin, an end, and an operator ++. Whoop, here, operator ++.
is there any reason to use iterators?
Yes. Iterators, I would recommend to use iterators outside of indexes unless you actually know the inside structure, because going to the next element might not be the next one in the list. So for example, if you use a linked list, which I don't recommend you to do, but if you use a linked list or if you use a map, for example, the next one in line isn't the next one in memory, right? So it's the container that tells you that if you want the next one, I know where it is because I'm the container. And these are not expensive things, absolutely not. Like, again, if you're thinking about like performance and if a thing is expensive or not, measure, right? And what they found, like you think of the high-speed trading firm, the thing that really wants things to be as fast as possible, they use this because it doesn't matter. It turns out to be nothing, right? All right? You good? Good. Go back to here. So, value semantics is the next part I want to talk about. So, let's talk a little bit about values. Stand up. So, have you been taught L values and R values? Right? A little bit? So this is going to be a crash course. Good. So, there are two ideas in C++. Well, there are more, but let's start with two. There's an R value and an L value. An L value is something that has a memory address. It's somewhere in RAM, basically. But an R value is something that is temporary. Either a literal, like just the number 10, if you type the number 10 somewhere, or it's an expression, like A plus B. A has a memory address, B has a memory address, but the result of A plus B is an R value, because that idea is temporary. It's going to go somewhere. It's usually going to go to an L value, but that idea is temporary. Same thing if you call a function. The function has a value, it's returning a value, but the thing you're going to assign to the variable while it's alive there is an R value. So again, yeah, we're talking about this. The thing that has a memory address is an L value, and the thing on the, so it's the left-hand side and the right-hand side thing. It's a nice way of thinking about it. There are more values, and C++ nerds really argue about these kinds of things. There's like a diagram of like a PR value and a GL value, and like no. Start with this. Thing with memory, thing that's temporary. You're good for now. So, we see the stuff on the bottom? I hope so. I have a class. I'm going to call it loud, because it's a loud class. Oh yeah, for those who, I don't know how new people are, structures and classes, same thing. There's no difference. So I have a class called loud, and I want to make it called A and B. And then the class itself has a constructor and a destructor. And when I construct the value, I just print out loud and then what the value is. And when I destruct it, I say loud with what the value was. All right? So these classes are actually very helpful for you to learn how the language works. Because when a constructor is called and when a destructor is called, it will print out. So you can see the order of things that are happening. Okay? So who can guess the order of this application? We make A1 and B2. So, interaction, what's going to happen? Yep?
It's going to print from the constructors in order first.
Yep.
And when the function goes out of scope, it will destruct the objects and print from the destructor.
Yep. In what order will it destruct?
That I don't know.
So, you're right in the first part. So we say loud 1, loud 2, but then we destruct 2 and then destruct 1. So when objects are created, they are created in order, but when they are destructed, so when the scope exits that they live in, they will destruct in reverse order. Yep?
That's because they're on the stack, right?
Yeah, they're on the stack. So you push onto the stack and then you pop from the stack. This is also helpful because loud 2 is created later and it might use loud 1, right? So if you want to destruct it, you want to destruct the usage of loud 2 first and then loud 1. So that can be helpful as well. Okay? Everybody got this? Cool? So, I'm actually calling that constructor with an R value. So I'm saying that the line 1, A1 and B2, the 1 there is an R value that then goes into the constructor loud int value, and then it turns into an L value, and then I'm using it, right? So we have these different value categories. Why don't we give the control to the programmer of which value category we want to use? So this matters when objects are being created from. Like, not that they are being constructed. This matters when they're being created from other objects. If I'm constructing from an R value, I might not care too much. But this matters when objects are being created from other objects. Okay? So, who here has heard of std move? Oh, we have scattering of hands. So this is a funky function that, yeah, even people who call themselves self-experts use wrong sometimes. So, for many, it's a mysterious function, but it's actually pretty boring. Because the classic joke for std move is that std move doesn't move. That's the classic one. Good one-liner there. Like another joke about Cplusplus is Cplusplus is really good at naming things wrong or getting the wrong initial name for things. So if you see a thing that's called something, that's probably not like a vector. Why is a dynamic array a vector? Like for me, a vector is like a direction, especially for you like game people, like that's a direction. Like, yeah, doesn't make sense. So std move, you can think of it as a signal to the compiler that the value you gave it is going to expire soon. Okay? We aren't going to use it going forwards, and whoever's going to receive the value can steal it, and anybody who is trying to use the value afterwards, it's been moved, that's not allowed. So this is why it's called move semantics or value semantics. So the only thing std move does is that it turns a value into an R value. See, I love that. Ah, I love those moments. Love those moments. Or to be more precise, it makes an X value. I think of it as an R value, but if you want to be technical, it's called an X value or expiring value. Because it technically still has a memory address. It's still there, but it's going to expire soon. So this is CPP reference, a screenshot from that. I recommend that site if you're searching for anything. It's very techy, it's very like standardese, and it can be like, it's an acquired taste to try to read it. And this is like a nice screenshot from it, because it's very like text heavy and bulky. And, but yeah, good. So using a value after it's been used with std move is not recommended, right? I like to think of it as like a zombie. It used to be a human. It still kind of looks like a human, but please don't interact with it. That's not like, yeah, don't do that. And again, the techie, unless otherwise specified, all standard library objects that have been moved from are placed in a valid but unspecified state, they say. It's still, the object is still there, but yeah, we don't make any guarantees about the state of the object. Again, meaning the object's class invariants hold and preconditions and that kind of stuff. So you can still kind of interact with it, but don't trust anything that it's doing. So don't trust the zombie. So, I can show you some demos. Too many things open. Here. What did I say? Part 2, example 1. And I have the terminal. Part 2, example 1. So here I have the loud class. And I also have, so I have in line 5, I have the constructor, which will just print out loud. In line 8, I have the copy constructor. You should have seen that one, I think. So the idea here is just, I'm given another class of my same type. I would like to copy whatever they have. They will still be alive, and then I will copy whatever they're doing. And then in line 12, we have a move constructor. So the move constructor is, what I'm being given is temporary. And I'm allowed to steal from it. That's the idea. The thing that I'm given is going to expire. It's not going to live anymore. it's very morbid to say, talk about it this way. It's gonna die, the thing is. So I'm allowed to do whatever I want, right? And then I have the destructor. And then I have a value. So I have the same before. I have in line 24, I have A1. In line 26, I just make a value and I give it over. In line 29, I'm making C by copying B. And in line 30, I'm making D by moving from A, right? So I'm saying A is going to expire. So basically anything like using A here is not recommended because it's been moved from. So that's the idea. So if I run this, terminal, example 1. So who can guess? Who wants to be brave and make a guess? Well, what will output here? If I can show you. So we're making loud A, then in 27 we make a B, 29 we make a C, and 30 we make a D. Nobody brave? Ah, shame. There we go. So I can keep it like this. So we make a loud 1, we make a loud 2, so that's 24 and 26. That's what we saw it before. Then we have 29. We copy loud 2 because C is equal to B, so we're copying it. In 30, we move loud 1. That's the move here. And then we're destructing. Well, we're destructing in a weird order, at least it looks weird, right? We say loud 1 is destructed first because that's D, because it's copied from A, right? And then the loud 2, because there's copies of B and C, and then loud 1, which is the A from before. Welcome. And I can show you that if when I move it, I can say L value is equal to 0. Because it's going to expire. I can do whatever I want with it. So if I run this, you see that A has not been modified. Because D was allowed to do whatever it wants with A. Because we are telling the compiler, move whatever A is into D. And after that, A is gone. Right? That's the only thing you kind of need to know about move and kind of these move semantics. And again, it's not move syntax, it's not like, it's semantics. And that's the important bit here. I think I also had, yeah?
Theoretically, does this mean that if we have like several loud classes, and we do what is not recommended, and have several of them, then have like the X value constructor using A. Does that mean if we change A using one of those constructors, we'll change the A value in every single version of cloud?
It depends on the order it's being executed, but you can think of, if I go back to here, once this line here has been executed, then you cannot trust A. Whatever A is unspecified, right? So if anybody else, if I say loud, we see the E, yeah, and not, if I do this, this is not allowed. Like, it will compile, but this is not what you want. This is not the idea you want. Because again, now, after it's been moved, you're doing it with a zombie. Okay? And the same thing here. Oh, not this, whatever this is. Same thing here. This looks fine. I think it will compile as well. But again, you're dealing with the zombie. Once it's been moved, don't trust it. There might be stuff there. There might be values. It might look okay. But it might work differently between compilers. It might do different things if you just change the surrounding code. So again, this is not why it's move syntax. It's semantics. It's once you've done this, don't trust what's there. Right? So that's more of the idea. And I can show you a more concrete example. Whoop, not going to keep that because that's not good. What if instead of a value, like I had an int as a value, right? What if I have a vector, which is a standard container? So they have implemented all this stuff for us. So again, I have value, I'm just resizing. I'm just using the size of the vector as the value for myself. That's fine. I have the constructor. I have the copy constructor. So here in the copy, I'm actually copying the vector. I have a vector of some values. I'm copying it to another one. But here, because this is the move constructor, I'm allowed to behave differently. Because the stuff on the outside is going to go away. So I can do different things. Because here in the copy constructor, I'm not, like you see, it's a const. I'm not allowed to change L, which came from the outside. I'm only getting a copy, only getting a reference to it, a const reference to it. So I can copy, which is expensive. But if I know that whoever's on the outside doesn't need this anymore, I can steal it. So a values.swap is actually very efficient because the only thing it's doing is swapping out the pointers inside. There's no copying done. You're actually getting the actual vector from the outside. So if you have a vector of one thing or a vector of a million things, this is the same size. So if we're talking about big O, for example, this is big O1. So this is O of n. This is O1. Because it doesn't matter how big the vector is, the swap is always the same size, the same speed. Okay? And this is the same thing here. We get the same thing. Okay? Any thoughts? Yep.
Seems cool and useful if you're trying to write efficient code, right? Because that means you don't have to copy the. That means you don't have to run the constructor for some other object to copy it.
I will show you more cool tricks later. There's more cool tricks with this later. And like, you're in the industry of making games. There are parts of your game that really need to be efficient. Like this thing here, whatever you're doing, like the main loop or some, like you have 16 milliseconds. It needs to be really efficient. So you need to think about these kinds of, like you need to design it in a way where you're taking advantage of all this kind of stuff, right? But there are other parts of the code that doesn't need to finish within those 60 milliseconds. Like a button being clicked or some background task or whatever is happening, right? Like adding up an experience value, like, okay, fine. But like initializing a new level or dynamically loading stuff based on where you are in the level, right? That needs to be really fast. So you need to think of these things. Okay? Cool. Want to see more cool stuff? Yeah, good. I don't have any more. No, I'm kidding. So, cache. This is going to be more of a rambly rant. So, let me see. Modern CPUs not only have memory caches, but they have multiple layers of memory caches. And the idea is simple. Let's put some of the data we think the program is going to use closer to where it's being used. And when I say closer, I mean, yeah, physically closer. Right? So I have some data in RAM. I think I'm going to use this bit of data. Let's put it near the CPU. The idea is as simple as that. Right? So you'll have RAM, but then there's usually a shared level 3 cache that's used by the whole machine. Then each CPU or core might have a smaller level 2 cache, and then an even smaller and even closer level 1 cache. And these are in like kilobytes. Okay? So how do we know what data the program is going to use? And this is a classic example of RAM. You have a list of things, list of values. So imagine this is RAM. We have some values there. And this is your CPU. And within the CPU, there are other slots, which are called registers. And these are the slots that are actually using the value. So if you looked at the assembly code, there was like an add something something. Where you're loading that from is from the register. It's not from the RAM. Or even the cache. It's always from the register. So it always needs to go to the register, do the work, move from the register, move into the register, do the work, right? That's your work desk. The cache is the next desk over, right? So I would like to load this 5. Cool. I put it in the register from RAM. I do some work to it, turn it into a 1, and then put it back into RAM, right? Cool. So from CPU to RAM, it's about 100 nanoseconds, roughly. I'll show you more numbers later on. But you can think of that as like 100 nanoseconds. So what if we have a level 1 cache just actually closer to the CPU? And what computers actually do, which is called locality of reference. When you want to load the number 6, it does not load just the number 6. It loads a block of memory around the number 6, right? Because it's likely that after you've used the number 6 there, you would like to use number 7 after that. So think of loops, think of arrays and vectors. There's a classic, like, I'm going to make a for loop, I'm going to use value 1, and then when I'm done with that, I'm going to use the second value in the vector. So once you've loaded the first one, the second, third, fourth, fifth, whatever, are probably already in cache. So you pay for the first one, which is why things like linked lists are not great, because you load the first one, the computer will load a bunch of stuff around it, then you want to access the next one, it's somewhere else in memory. You don't know where it is. So it will load that. So you always take a cache miss, it's called. And when we load 6 and do whatever work we want to do, and then we want to load 7, and 7 is already there, that's called a cache hit. It's there. So we load all of them in. I put 5 in. I do some work to it. I put it in the cache, and I save it there. And then I would like to load 6, but it's already there. Cool. I can do something with it. So L1 is about a nanosecond. These are tiny numbers, right? This is not much. Yep.
So if I want to use 5, 6, and 7, I want to load 6 in.
Don't. You can do tricks if you know exactly what CPU you will be loading, right? If you're on exactly this CPU with this instruction set and compiling with this compiler, yeah, you can do tricks. Absolutely. And again, this is the nerdy bit of it. Like, ooh, what if this thing? What if that thing? But think of this generally as like, I want stuff to be next to each other, right? Yep.
So, like you say, like 100 nanoseconds and 1 nanosecond, but isn't that like wildly varying from PC to PC?
Oh, yeah. I'm just giving you a scale. Yeah. All of these numbers are probably outdated. And like this, if I would measure, this number would not be the same from one run to another as well. So just to give you a sense of scale.
If you're going to build a PC, like what decides the speed? You know?
There was a joke by one of my professors that kept saying, if I could make a PC out of just cache, I would. But you can't. That's just a size thing. I would recommend looking up like IBM PC diagrams of like seeing, because they are literally like you have the core and you have everything, and the cache is like in the core. It's like there. So it's just part of the circuitry of the actual machine. And usually if you're like buying a machine and it will tell you like, oh, the cache size is 8 megs or whatever, that's usually what you hear nowadays, that's L3. You usually don't see L1, 2 specified. Unless you go into the specs, then you'll see L1 and 2. Because the L3 is the one they can sell, like, oh, it has 16 megs of cache. Like, okay, cool. Yeah. Okay, yeah, and then you have 32K, 256K, 8K, like it's just sense of scale. Like the level 1 is very small. But it's still like it's pretty, and usually some machines also have like a separate data cache and a separate instruction cache. Like your code is in one cache and your data is in another cache. I think AMD does that a lot. Okay? Oh yeah, some numbers, just a sense of scale. Yeah, you have CPUs, and then the cache is just there. L2 is also somewhere there, and then 3 is shared between all of them. Kind of the, if you want a mental model, this is fine. This will get you pretty far. Okay, so why does this matter? Again, we're doing game stuff. Here's a zombie. We talked about zombies before. And this zombie has a position, X and Y. They're somewhere on the grid. And I have some code. I have a for loop here. I'm moving the zombies around. And another joke is it's X movement and Y movement, so they all move the same, right? No? Okay. Fine. So if we think of, like we have memory, some memory addresses, and we can think that 142 and 12 is one zombie, 11 and 19 is one zombie, 521 and 72 is another zombie. So we have 3 zombies there. Because that's how this is laid out. If you have a vector or an array of this this class, they're just right next to each other, like literally, and there's no space, there's no extra junk, there's no stuff, right? It's just there, okay? But then you're like, it's really nice if zombies have health, right? We kind of need zombies to have health, because we're going to shoot the zombies and then, right? Because then you're pushing, you see the 11, so now in 0x100, we have the health, right? So we have the same position, and now we have the health. So that class is taking up more space, even though in that very important loop, we're never using the health. And if we think about the locality of reference back, if I would like to load 0x092 to get the x value, I'm loading into cache 96 and 100 because they are next to it. So I am technically loading the health into cache every single time. And then you keep growing the class, right? You have the model or the AI controller or whatever, right? You keep doing this. Yep.
That's why you mentioned that you shouldn't make the class if it doesn't require it.
Yeah. Or you can. Sometimes a thing I see sometimes in games is you might have this class, and this is fine, like it's the zombie, but then you want to do zombie movement. Like, I would like to process all of the zombies and make them do the movement. Instead of using this class to do the movement, you might take the hit of copying the x and y values to a zombie movement class that only has the x and y values. Then use that class to do the movement, and then take the hit of copying the data over back. Because once you start copying it over, that's going to go into cache. It's actually pretty quick. And then you're going to do the loop that you've measured is slow, like you've noticed that this is slow. You do the thing, then you copy the data back over. Yep.
So that will make the cache smaller, but wouldn't it make the process take longer?
Here's the thing, no. There's another trick that people sometimes do. If they have a linked list of things, this is just an example of why the cache matters so much, right? That I've seen examples where if you have a linked list of like 1 million things or something, and you want to loop through the linked list, and then you might say like, we need to sort the linked list. And to sort the linked list, you need to go through all the elements and do all this kind of jumping through hoops. Like a lot of cache misses that are happening when you're sorting a linked list. It's faster in some cases to take the linked list, copy it over to a vector, sort the vector, and make a new linked list than to sort the linked list. Because the cache has such an effect on this whole thing. Like, again, we go back to if I can make my computer just cache, I would, right? So this is the counterintuitive thing. But again, if I go back to the things I've been saying, measure. If you don't see, if this takes a nanosecond and nobody cares and this is instant, leave it alone, right? But if you see that the problem is here, the problem is that this class is too heavy and we're only using this, then you can try copying the data over, using only that, copying it back. And you can see an improvement on that. Yep. Cool. So, cache is fast, and I'm bound by programmer law to show you this. Again, these are just numbers for scale, so don't take exactly the numbers as gospel, but L1 cache reference, half a nanosecond, L2 is 7, main memory reference 100, sending 1 kilobytes over a gigabit network, 10,000, reading 4K from a solid state disk, 150,000, reading 1 meg sequentially, 250, read 1 meg from a disk, 1 million, disk seek, 10 million, and sending a packet from California to Netherlands and then back, 150 million. So 150 milliseconds, okay? Again, scale. Think of scale, right? And humans are really bad at this. Because how much bigger is an L2 cache reference versus sending a packet? Right? Can you see the scale? Because if an L1 cache reference is a heartbeat, so I'm going to scale things up, right? So now it's a half a second, okay? That means an L2 is 7 seconds, or like a stretch. A main memory reference is 100 seconds. You're going to make coffee. So would you rather have a heartbeat, reading a value every heartbeat, versus reading a value and you have to make coffee every time you read a value, right? Sending a 1 kilobyte packet, that's 3 hours. You can watch Oppenheimer. Recent references here, huh? Read 4K from a disk, that's 42 hours. It's a weekend getaway, right? Read 1 meg, 70 hours. Read 1 meg from an SSD, that's 277 hours. That's a 2-week vacation. Versus a heartbeat, right? Disk seek, 115 days. That's a semester plus a 2-week vacation. That's what you've been doing now all semester plus a 2-week vacation if you want to read from disk, which you do every day. You're always reading from disk, right? But that's just showing you how fast the L1 cache reference is. Sending a packet, that's 4 years, 9 months. You can earn a degree, you can start a family, you can start your career. That's sending 1 packet, right? So again, humans are really bad at this. So if there's one thing I want you to take away, cache good, RAM bad, right? Good. So again, instead of every time you want to read a value, you have to make a coffee, and then you're allowed to read the value. But you can otherwise always read it, right? I mean, you do this every day. Like if every time I wanted to switch a slide, I would have to walk over there, right? Versus doing it just here. This is the important bit. But that also means that you need to know the structure of your code, the layout of your code, what is where, right? And again and again, if you're not seeing the issue, it's fine. Just measure it. Always measure it. Yeah, we want stuff in our cache. We also want to be aware of how memory is laid out. Yeah, what I said. So here's another visualization of this kind of stuff. I have a zombie. I would like to move the zombie there. It's usually done by moving X and Y, right? And this is the zombie value. And they're somewhere in RAM. So I'm going to show you some assembly-ish. So I would like to load memory address 100 into A. And A is one of the registers the CPU has, this hypothetical CPU. Cool. That's an instruction. We can do that. And then, whoop. Okay, that's what the one extra slide there. Yeah, and then I modify it and then I write it back. Okay. Then I want to load 4. I increment it by 1 and I store it. So I load 104 in. I add 1 to it and I store A in 104, right? And then it increments by 1. So we have this bit of RAM and we have a bunch of zombies somewhere, right? So if you're doing this in a loop, again and again and again, you're loading the number, adding 1 to it, storing it. You're loading the number, adding 1 to it, storing it. That's what the assembly, like if you're writing this out in assembly, you can think of it like this. This is the thing that's happening, right? So what if I could reorder it? But that doesn't work because I'm always loading into A and storing into A. That's not great. So I need to load into different registers. Okay, so first I load everything I need to load. Load from 100, 104, 108, 112. Okay, cool, I have all my data. And then I want to add all the numbers. Cool, I've done the work. I want to load things back. Because now you group things into, this is the thing that takes time. Because this is the memory load. So again, if you think of the scale, because the work is basically instant. And again, this is expensive. So you group the expensive, the cheap, and the expensive. Okay? So this is not just a blank. This is a blank piece of paper. If you want to make a hole with a hole punch, who's used a hole punch recently? That's the thing I haven't used. Like, oh, you're in school. Okay, fine. Yeah, sure. You make people do hole punches. That's not fair. So you make one hole punch, right? You make the machine and do the one hole punch. And you use a tool like this, right? 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 No, okay. You might use, if you want to do 2, you might use a tool like this, right? Okay, cool. So you bring the item, you bring the tool, you do the work, and then you put it back. Where's the analogy here, right? Because what if you want to do this? And use the first tool. You have to use the tool and then use the tool, right? But what if you had this tool? You bring the paper, you do one clunk. You've done all of them. Who sees where I'm going with this? Yeah?
Parallelization.
Yeah. So, your CPUs are kind of neat. So instead of doing this, we load and lay out the data. So I lay out both the values I'm going to load for and also the operation I'm going to do. So I'm going to load from 100 into X, and I also want to load the value 1 into X1. So I basically laid them out as the data, the operation, the data, the operation, right? And then I do hole punch, and then I store the values back. And this, if you have a zombie, you have an X and Y, I would like to go through all the zombies and add up all the movement, like the loop that I'm talking about. This is sometimes the assembly you'll get. So you're doing the load, you're doing the expensive thing, and then the operation is one operation. And then the store is one store. So if people have been talking about like MMX or, yeah, it's called XMM there, these are features in modern CPUs where the compiler can figure out that the work that you're doing is similar work right next to each other. So the compiler will not create the initial assembly. It will figure out that, oh, you're actually doing this kind of operation of loading, performing the same operation on a list of things. It will try to pack these things together to do one operation on it. So that's also another benefit of using data structures that are next to each other. It's not only the cache that you're benefiting from, you're also benefiting from the compiler saying, oh, that means that I can line them all up together and do one hole punch, right? So, yeah, do that. Okay, how are we on time? Good. Only 1 hour. We're here for 4, right? No. No, I don't have content for 4 hours. So, part 3, part 2, right? That's usually what movies do, right? So, CPU. So what the CPU is then doing, and this is again, very generalized. They need to fetch the instruction that you want to do. You need to decode that line of assembly that you have. They need to execute that line of assembly, whatever that code bit of machinery needs to happen. You need to then access the memory to either save or store or that kind of thing. And then you need to write back the value that you had. So fetching, decoding, execution, memory access, write back. This is the thing that the CPU does for just one line of assembly every time. So if I want to add 5 into A, we have the instructions and we have units of time. So I'm even more abstract. This is just unit of time. So we need to fetch, and that costs us 1 unit of time. I need to then decode. That's another unit of time. Execute, write, memory, write, right? So it took us 5 units of time to do this. So if I want to then save whatever A is into B, do I then need another 5 units of time and then another, right? That means that the fetch part of the CPU is bored for 4 cycles. And then it gets to do one work. And then it's bored for 4 cycles. So instead, they pack them together. This is also why, like, when people talk about executing code on your CPU, that things are done in a strange order. Because while we're decoding A5, we're fetching add BA. While we're executing A5, we're decoding BA, right? Thankfully, when we're executing BA, we're writing stuff. So like the order is weird there. And then we can have a third one, and so forth and so forth. So it's usually called instruction packing, I think it's called. You want things to be as tight, like there's no gaps. Because what can happen is you can have this. It's usually called a bubble. So there was a stall or some other bit of instruction happened. Like, it's never this clean. It's never this beautiful, right? Even if your CPU is at 100%, it's not like this, right? And what it can also then do is it can reorder. It can figure out that, because B depends on A, I can actually do C9 before BA because there's no dependency there. So you can create this dependency hierarchy of all the execution graphs and whatever it's doing and find out that, oh, this bit of code can run whenever because it doesn't depend on anything. And this bit of code depends on some other stuff, so that needs to run first and then I need to run my code, right? So it's just a nice mental model for you. And then you have that in a package, that's a core, and then you have many cores. And then they can do their own thing. Right? So again, another mental model for you. Okay. Part 3, example 1. Mouse asleep, yep, there we go. That was, yes, this one. This is a fun one. If I go here, so here's my caveat for some of these examples. I've only tested them to be true. I don't know if they work all the time. Because with a lot of these like optimization things, they might do one thing on one machine and then I'm doing it on another machine. They might behave differently, so caveat emptor, that kind of stuff. But here's the idea. I have a vector of data. And data is a bunch of integers, and then the value that I want, and then a bunch of integers. So it's just some stuff before and stuff after. So I'm kind of polluting the cache, right? And then I reserve a bunch of things. I loop through and save the value. And then I have a clock, and I would like to sum up the value, or like add them up together. So in the loop, I'm only accessing value, but because of the cache, I am always loading these arrays here as well. So they're always being loaded into cache. The CPU might spot what I'm doing, because there's another type of optimization where it's not loading this thing you have in cache. I think it's called spatial. Don't remember the second part of it. It's spatial, because it's noticing that I'm reading a value, and then I'm reading a value 11 parts over, and then 21, and then 31. So I might notice that and then load those in cache, but we'll see. So it's the clock. I'm just taking the time that it takes to load. So if I run this, took 45 milliseconds. Let's run it a couple of times, 41, 44, and then I can comment out this. Yeah. So, so instead of taking 45 milliseconds to do the work, it took 2 milliseconds to do the same work. So it's a bit of difference. Again, this is an example, an exaggerated example, but this can impact your code. That this kind of behavior can sneak in and make your thing slower. Okay. So I run that again with the thing in. 43, yeah, because I'm always loading the thing. Okay? Any questions, thoughts? Cache good? Cache good, yes. Cache very good. So, this can be boiled down to a few tips. So generally favor data structures that are aligned linearly in memory, array and vector. And again, I say generally favor, okay? Generally avoid data structures that are not, like linked lists, okay? And accessing one data member of a class will also load some of the other data members into the cache. Okay? It's like a TLDR. Good. Thoughts? No. That means you're all experts, right? Yeah. So this is more of a passion thing for me. This can matter. This is not as big as cache, but this can matter, and this is more of like an interesting Cplusplus thing. So again, this is not as big as cache, but this is interesting. So there's a technical term within Cplusplus that talks about triviality. It can affect you, and not that many think about it or talk about it. And it does not mean trivial as simple. It does not mean like easy to read or easy to understand. it is a technical word within the specification, so it only means something within the standard. Oh, I had a demo immediately. All right, fine, fine. Yes, this one. Okay. So most of this code doesn't matter. It's like a timing code. This is the thing. So I have a user, and the user has an account ID, has a profile URL, company ID, email, and password, right? This is a classic, like some data class, right? And then the only thing I have is a destructor that does nothing. Seems fine, right? Destructor does nothing. I mean, what can it hurt for shadowing, right? And then I create an array of users, create some users. I loop through. This is just for timing purposes. And then I would like to copy this vector. This vector that I created here from the outside, I'd like to copy it and then do some work. I would like do stuff, right? But I don't need to do stuff to demo this. So this is just to prevent the compiler from optimizing this away, because I don't want to have like a bunch of code that does the examples. So think of it as I made a vector and then I copied it, right? That's a common thing, right? We have some data, I would like to use it, I'm going to copy it, maybe because it's coming from another thread or something, I'm copying it and then I'm going to use it. And then I'm just printing out the timing, right? Good. So let's go to part 4, example 1, right? Yeah, example 1. So this takes, so the average copy time is 0.0006, right? That's per copy, and that's the average. I've taken all of them, averaged them out. I've done this like a million times or something. So the average copy is not that much, but again, this is per copy, so every time you're doing it, you're taking one of these hits. Let's take out the destructor. So 0.002 instead of 0.006. That's weird, right? The destructor didn't do anything. Why? What's happening?
What changed?
Yeah. I took out the destructor.
Oh, right.
Yeah. But the destructor doesn't do anything. Weird. So. I'm going to do the whole thing there. Okay, that's fine. Yeah, here's another one. I have a player, right? The player is a constructor, has some items, has gold, health, whatever, has damages and positions and whatever. I do collision checks. I make a bunch of players. I loop through all of them. I check if they're colliding, and I count how many are colliding. That's the only thing I'm doing. And then I have damage type, which is something. I have an item, which is something, and a random position, which is random. Right? Good. This should take, I think it took 11 seconds. Let's see how good I am at remembering. 8 seconds. Okay? Oh yeah, this is an example of the cache. Sorry. This should have been the other one. So I'm going to take out everything. So we just have this. There you go. Yep.
Is this because of what you mentioned in the beginning, that even though you aren't using it, it's still having it in its cache?
Yep.
So
Yeah. This example should have been in the other one. In the other. Yeah. Yeah. There's a mistake on my end. This example should have been in part 3. But I'm just showing it now so we can have it. So with this one, example 1, let's go back to that one. What's happening here is triviality is the idea that you can take a class, and if you're copying it to another place, you are allowed to use memcopy, which is a very fast copy function that will take the bytes, the actual just zeros and ones from this location, and copy them over to the other place. And a class needs to be trivial, which is a certain specification, for this to matter. And by just adding a destructor or a copy constructor or a copy assignment operator, for example, the class is no longer trivial and you cannot copy it with memcopy. Because the compiler sees those functions there. And if those functions are there, they have to call them. So we can no longer take the actual zeros and ones, the actual literal zeros and ones, and just copy them to another location in memory. We have to construct every object and call all of the functions, because the class is no longer trivial. And there's a bunch of classes, even like standard library classes, that will make your class no longer trivial. Like if you have a std string, then your class is no longer trivial. If you have a vector, then your class is no longer trivial. If you have ints and arrays, then your class is trivial. And there are ways to test. If you want to go into that maybe later, there is a check to check if you can check if a class is trivial at compile time. So you can check for those things. But this can matter. If you have a class like a data class that is being copied all over the place and being moved around your code base all of the time, and it has like a string or a destructor or something like extra, then you can have a big performance hit. And we actually had a performance hit in a thing like this, where we had a class that just had two IDs in it, which were the two people talking in a conversation. And anytime people were talking, these IDs were copied all over the place. And someone added as a destructor to that class, which wasn't needed. And the system went down because the performance hit was so high that, yeah, you brought the system down by doing this. So this can matter. It's not a big, as you saw from the timing thing, it's not like a factor of 2 or whatever, but it can matter. So if you can keep your stuff trivial, make it trivial. Yep.
Let's say that in our case here, we have to have the destructor for some reason, right?
Yep.
How about if we make a new class with the rest of the arrays inside of it, and our main class has a pointer to that class?
Yeah, you can do that, yeah. Yeah, there's an idiom as well, it's called pimple, where the implementation and the interface you use are different. So you can have that. And again, measure, where you can have like the heavy thing, the thing that's actually costly to copy, have that somewhere, be trivial, and then you can have a pointer to it or a vector of it or something like that. That's fine. Like you're taking the hit on the main class, but the actual copy is fine. Mm-hmm. Yep.
So is the reason why array is so much like less because vector is more flexible and therefore needs more space?
Yep. The thing with vector is because it's a pointer and 2 or 3 iterators. That's the only thing inside of a vector. Then it points to somewhere else. It needs to have a destructor to be able to delete that dynamic memory. And because it has a destructor, it can't be trivial. But array is just a list of things right after each other. Like an array of int 2 is the same as having 2 ints. And someone said that you actually gain value from having, if you want to have an array of 2 things, you actually gain information because now you also know the size. Because the size is baked into the class. It's not in the type. So that's another benefit you have, yeah. You actually get the size for free. So another general hint, if you want a list of something and you know the size, don't use vector, use array. And if you want to use a vector and you kinda know the size, like, oh, it's gonna be 100 or 500, right? You roughly know the size, reserve that memory. Like if like I'm doing here. Instead of resize, do reserve, like this. Because if you don't do that, the vector is empty, and then you add one item, so it allocates the one item, and then you want to add the second item, it creates a new vector internally with size of 2, copies the first item into the new one, deletes that, and makes the space for the second one. And then when you want to make the third one, it makes a new one with 4, copies the 2 over, makes a space for the third one, and then when we add the fourth one, it's free. When you want to add the fifth one, it makes a new vector of size 8, copies the stuff over. So by just adding 5 items, you've actually made 4 vectors. So even if you like roughly know like, it's at least 10, right? It's probably in the thousands, but it's at least 10, right? Making a reserve a little bit, it can actually benefit you. Again, measure. And this is I want to resize, yeah. Okay? Cool, that was trivial. Moving data. We are good. And yeah, and not that kind of move. Generally, when you're writing code, you would like to isolate work into functions, right? Yeah? Yeah, you should. It improves readability, testability, and general sanity of everybody around you. Don't think that writing a function costs you anything. If you're going to use it once, it's still okay to write a function. I have never seen a actual big performance thing that says like, oh, it was actually costly to have a function. Like I've once seen kind of an example, but that was like a dynamic like allocation of a function. That wasn't the calling of a function. So don't think that calling a function is expensive. So that means that sometimes you create the data in the function and then return it out, right? You can think of this code, right? So I have main, and I have a function called createValue. And then I have a value, and I return it, right? Good general idea. And I have this function, createValue. The result is 10, but if the input is more than 10, I increment those together and return the result. This is just some, like the function doesn't matter, it's just some logic, right? If something, I return a different value than the other value, right? Everybody good? Good. So what if it's an array? Because this, nobody worries about this. Yeah, you just get the int out, right? It's 4 bytes, nobody cares. What if it's an array? So I'm doing the same thing. I have a function. Instead of an int, I have an array of 10 things. If it's greater than 1, I change the first value to increment, okay? And then I return the result. Is this bad? Is this good? Is this fast? This is slow? What's your instinct when you see this? What's your like, oh no? Or is it like, that's fine? Yeah? Personally. What about impersonally? Yeah?
I would imagine that the if statement prevents the compiler from packaging the information easily.
Yeah. Again, this is good gut feeling. Because when people see this, they're like, oh yeah, not a problem. Because it's for those who don't know, how return values are done, that it's just a slot that's allocated in the stack. And then this is written into that slot. So we have an array, the slot is bigger. It's just the more you write into. Okay? So you huh?
The slot is
bigger. Or sometimes it can be like, the slot is a pointer that points to another point in the stack, and yeah, but mental model, slot is bigger. So, okay. So what if I print out? So here in the cout line, I'm printing out the memory address of result, and here I'm printing out the memory address of value. So what do you see in this result out there? Tell me what's happening here. Any thoughts? Yeah?
It's looking up the value in memory, in RAM specifically.
Yeah, it's the same memory address. Why? Why is the array in there the same memory address as the array out there? That's weird. Because even if it like would happen to be in the same place, when you call a function, there's more stuff on the stack that you have to pop, so they wouldn't align up. It's because in the way I wrote this function, the compiler noticed that the return value is always the same variable. So instead of creating that variable up there at the top, It doesn't create it. It uses this one. So when you call the function, when I say result 0 input, I'm not modifying the array up there. I'm modifying this one. What? That's weird, right? That's only because the only way to return out of this function is with the same variable. So there's only going to be one variable that goes out of this function, and only one variable that is going to be assigned to. So why bother making that variable up there? Let's make it out here. So this breaks if I do this. If in this case it should be an empty array, but in the other case it should be an array with stuff in it, now you see there's a different memory address because it's not the same variable being returned. So this is called return value optimization, or sometimes called copy elision. C compilers are allowed to do all sorts of optimizations, and one that can impact how you write your code is called copy elision, or return value optimization. So, in general, the C++ standard allows a compiler to perform any optimization providing the resulting executable exhibits the same observable behavior as if all the requirements have been fulfilled. It's called the as-if rule. As if. So, there are many types of RVO, return value optimization, but the one you would probably hit the most is called NRVO, named return value optimization. And a quick way to remember it is if the same variable is the only thing used in a return statement of a function. Okay? So, in this case, do we have RVO, NRVO? Yes, no? 2 hands? 3 hands? Yeah. Yeah, we do. Because it's always the same variable that's being returned. Do we have an RVO? Yeah? Yeah, you can modify it. So if in this case, if I create a vector and I put stuff into the vector, but then something happens, if something, it doesn't matter what it is. So if something happens, I want to back out. I want to undo. I want to give the user back an empty vector, right? You can still clear it. That's fine. You can modify it all you want as long as the same variable is in the return value. That's fine. So who has used std optional? Std optional. So std optional is basically like, it's called a maybe type. So data is some class we have, but optional is a container that contains our class, or maybe not. Yeah. So instead of returning a null or a 0 or whatever, you can return a std optional, and then you can ask on the outside, is there a value here? And then you can get the value out. This is very nice. This is very, and all the same optimizations happen here. So instead of a vector of things, you can have a thing or maybe not the thing, right? And this is very good because, again, we make a data, we create the data, but then oops, something happened, and I want to return a null optional. I want to return an empty. Yeah?
Is that similar to nullable data types in
Yeah.
C#?
Yeah. Very similar. And you can ask like hash value and get the value out, and yeah. So here, we don't have an RVO because in one return, we return a std nullopt, which is some other thing, and then the other one we return result. So we don't have it. So instead, you could do this. You set the value, but then oops, I regret, you can say reset, and then return out. So you then get a null out. So there is a caveat though. Be careful with returning references. So if you have a value, and then you create a new variable, which is a reference to another one, and that's the one you use throughout the thing, it doesn't work. You should create a variable and use that. Don't use the references, because they can break it. This only works because we're replacing the return value slot. It's return value optimization. It doesn't work with references. So here, for example, I have the same idea. I have an array, and I'm printing out the memory address. And then I have an array with some stuff in it, and then I have a result, which is a reference to the array, the data array. And I print out those two memory addresses. So those two refer to the same memory address, but on the outside, I don't get that one. because the compiler sees that, oh, what they're actually returning out is result, which is a reference. So I'm not allowed to do it. Okay, makes sense. And the memory model you can have is like it's return value optimization. So you might think like, okay, that doesn't impact me, but if you use structured bindings, with a structured binding, if you have a pair, you can break out the pair into two variables. So in this case, you say like, hey, we have an x, I print out the memory address, I return x, and then I do the data. This also doesn't work. Because a structured binding, you make a variable, and then you get a reference to the two things. Back from break. Everybody well rested? 4 more hours to go, right? No. So I have a little bit left here, and then I have a talk I've done previously, which is more gaming related, which is way more silly. So we're going to have a bit more fun afterwards, and we'll do some game hacking. Who's ready for that? Yeah? Yay, hacking! So, this is like more Misc, where I couldn't like find, because all of this have been like, please think of cache, please think of like triviality and think of your classes, and like I've been going over like this kind of stuff. There are other hints and tips and tricks that I couldn't like fit into a whole category. So these are like, yeah, Misc. Try to use standard library containers and classes when you can. It might, again, we have the pragmatic brain and the nerdy brain. Like the nerdy brain wants to implement vector again. The nerdy brain wants to create their own like sorting algorithm or whatever. But yeah, try to use the standard library containers and classes when you can. Try to use the stack and not the heap when you can. Again, if you have to use the heap, that's fine for dynamic memory, but try to use the stack when you can. If you need to use dynamically allocated memory, use things like std vector and std unique pointer. Who has used unique pointer? Yeah? Good?
Well, what is the difference between unique pointer and just normal pointer?
Yeah. So, okay, so you've been learning about normal pointers. Unique pointer cleans up the memory after itself, so you don't have memory leaks. And there's no cost of, like it's the same cost as allocating, it's the same as using it, but you just get the cleanup for free. And you use std move to move it around. If you want to give it to a class, I can show you. There's another one called shared pointer. Shared pointer counts how many other instances have access to it. And when the counter reaches 0, when it wants to be destructed, then it deletes the memory. But only use shared pointer if you're actually sharing, like between threads or between things. Like if you're actually sharing the data between things, then you can use shared pointer. Try to use unique pointer when you can. So here, for example, here's make unique. I want to make unique int 20. So I make a unique pointer. This is a pointer on the heap. I have some data. And then I want to use the data. I want to send the unique pointer into that function. I need to say it's to move into the function. Because that's how unique pointer works, is only one scope is allowed to own the data at a time. So if I want to send it somewhere to another scope, like a function, I need to move it over there. But that also means, because we talked about move earlier, now using data after this int result line is not recommended. Because this function now owns the data. And when the function exits, then the data is deleted, not when the main exits. And then I can use the data or do something with it. Then I can dereference it like a normal pointer. Okay? And then you can't use data here. It's already gone. Okay? So this is very, very useful. So I'm guessing you've been learning about like new or I don't know, malloc. What have you been learning? Yeah. Don't manage memory yourself. Let the language structures do that for you. Like use unique pointer, use vector, use like those are allocating memory for you. Constructors and destructors are your friend, and if a destructor is causing problems, like in a loop, then move the object one scope higher. Because destructors cost time. They take time to execute, like any code. You need to deallocate the memory. But if that is costing you time, like you're allocating the memory, you're doing some work, and then at the end of the loop, you're deallocating the memory, and if that is the part that's costing you time, move it out of the loop. So the work in the loop is the work that is being used. Who has heard of emplace back in a function? Because if you have a vector, you do pushback, right? So there's also a function called emplace back. So if I have a player, x, y coordinate, I have a vector of players, and you can do this, of course. Players, pushback, and I can make a player, right? I can construct a player with 10 and 20. This works. You can say emplace back player 2030, but that's not what emplace back is for. Emplace back is to do this, where calling emplace back is actually calling the constructor of the function. So instead of, because you might be creating the value here. So if this is expensive, you're creating it here, and then you're copying it into the vector. So you're doing it twice. Like you're creating the R value and then copying it over. Why not just create it in place? Emplace. Again, it's an awful name. I don't like it. But so it's being created in the vector when it's being added. So you don't have to worry about that allocation. So that's a useful one. That's why there's two of them. This pushback, which is you take an existing value, usually an L value, and you copy it in, and place back, you construct it there. Yes?
How would the class look list after the emplace?
Same. Like the players pushback player 1020 and players in place back 2030, it's the same thing. This here acts like the constructor. There's a compiler, not a compiler trick, there's a language trick. I don't remember what it's called. There's a thing within the library where you can call the constructor of the object, or you can make it look like you're calling the constructor of the object. So they look the same. That was what you were thinking of, right? No? Okay. But yeah, and place back, creating it in place. So I have a thing. I save some data. Okay, I have a constructor. I have some data, a number, and I create it there, right? Seems normal so far, right? And then I do this. Inline int operator parentheses, and then another parentheses for the value, and then in that function I return data plus value. This is called the call operator. You can have an addition operator, you can all sorts of operator overloading that's happening. There's also the call operator, which means I can use this object, like a function. Okay? So you can create these. If you have a class and you would like to use the class like a function, you can overload the call operator. Okay, so what's interesting about this? Well, who has used lambdas in C++? Yeah? So here I have a lambda. It's a thing. I have so in a lambda you have the capture. I'm capturing data from the outside. This is the argument to the lambda, and then the data, and then I call the thing, right? Because that's how lambdas are implemented. It's a class that's overloading the call operator. And then I have the constructor and I have data. This is the same thing. So this is lambda. This is how it's implemented. This is why tools like CPP Insights are important, is they allow you to see the underlying thing that's happening. So lambda isn't anything magical, it's just, it creates this kind of thing. It creates a class called lambda 418. Who can figure out why it's called 418? You can't actually call it and name it, but because it's on line 4 and 18 characters in. That's it. Okay? So, a couple of years ago, I asked Twitter to give programming students some advice. I got 709 replies. Everyone from students themselves to the principal software engineer at Cplusplus for Google. You want to hear some advice? No? Okay? No. So, don't worry, they were nice. So, become obsessed with testing your software, revel in finding ways to write code, verify how code should behave, do it at every layer you can. Write pervasive, fast, and reliable tests, and run them continuously. All right? Fight for simplicity. It'll be a huge fight every time. Whenever you do, it will be a benefit if you win. The wins will usually be invisible and uncelebrated, but they are worth it. Be intentional about the levels of abstraction in your design. Don't design components to be reusable in general if you can't see them being reused. Again, pragmatism. When designing for reusability, constrain your solution. Don't make it too general, right? That the class, they can do everything. Like, no, they can do the two things. Play, have fun, do stupid things, follow advice, explore your own ways, and also ignore advice. Yes. But yeah, reflect and think, and why does it work? So yeah, make mistakes, please. Read code. This is a good one too, because yeah, you're going to have to read a lot of code in your life. Best way to do good design is seeing lots of different ways how to do things. Don't worry about architecture at first. Analysis paralysis is real. You don't know what the good code is after experiencing a lot of bad code. He says different code, but I know he means bad code. Try to make the simplest solution that could possibly work. Don't consider efficiency or any quantitative characteristics except small and dead simple code. Get it working and then. So again, measure, measure, measure. Just get it out there and then measure. Because so often I've been writing code, I'm like, oh, I'm worried about this kind of optimization. And then I just try it, and like, no, it doesn't matter. It doesn't actually matter. So, do top-down coding on the way down and bottom-up coding on the way back up. This is more of a joke. But, I recommend his talks, Tony Van Aert. When he talks, he doesn't talk often at conferences. He has a lot of videos on YouTube. He's very strange, because he doesn't like doing the same talk twice. So once when he had to do the same talk twice, he made the whole talk rhyming. So the whole talk is one big poem. Yeah, he's great. Yeah, so, and then I, of course, did some analysis. 131 out of the 763 tweets talk about people, so 17% of all the advice are about humans and people and peers and friends and like collaborating. 10% are about basically like learning or practicing. 13 of them were literally never stop learning. 27 talked about mistakes and failing. 29 talked about fear or being afraid and scared. 34 talked about tech and algorithms and focusing on the big picture. And 33 are about personal health. It's get sleep, eat healthy, take care of your body, even if you feel fine. So yeah. And you can, if you want to look at the thing, it's just Olafur Waage program advice. It should be there. Yeah, it's from a few years ago. It's almost 5 years ago now. When Twitter was relevant. Yeah. Yeah, when it was Twitter. Back in my day. Yeah, it's my face again. Okay, so before I go on to the silly talk, any questions, thoughts, comments, rants, dad jokes? No? You're experts in everything now, right? Yeah, good. Okay, who wants to be silly? Who wants to do some game hacking? Yeah? Good. Good. How much time? Yeah, I think we did. I might go a bit fast, but we'll see. Nobody cares, nobody cares. Oh yeah, I like this one too. People say nothing is impossible, but I do nothing every day, which is, again, Winnie the Pooh. Yeah?
I have a question regarding like you using stack instead of the heap,
Yeah.
right? Because before I came here, I was at UIB, and there are programming teachers in like the efficient algorithm subject taught us to care more about like the big O time of your code instead of the micro optimization, which seems to be your approach for this talk, right?
Yeah.
So there we was taught to use heap instead of stack, because on the heap you can access immediately, like directly, instead of having to go through the entire stack.
No, you can access the stack immediately. You can access the stack immediately. That's same time. There's no difference if you have a stack or a heap. They're all the same RAM. It's all RAM. Stack is here, grows down. Heap is here, grows up. It's all in RAM. And the program scope is here. So if you want to access the value, you can access it the same way. The only thing with the stack is limited in size. So it only grows to a certain size, and then you can. That's why you have Stack Overflow, because it's a certain size. But the heap can grow and grow and grow, because it can grow from here, and then it can access memory elsewhere. But the reason why I'm focusing on this is the stuff I keep seeing. Like thinking if an algorithm is big O of n2, or if it's big O of n log n or something, like how, like I think I've like done big O analysis at work like 3 times. But the amount of times I've seen this kind of stuff break systems because they're not thought about is way more. Way, way more. So again, measure and like, yeah, don't use silly algorithms, but like the hot path of your loop, the thing that's running again and again and again, versus like, oh, I'm loading something and I'm doing it optimally. Like, what's the time scale here? How often are you loading the optimal code versus how often is your very silly little loop that's incrementing where the player is moving? How often is that running, right? Another way to think about it is, there was a talk from a few years ago that thought like, think of the execution of all your code as like a bunch of like zeros and ones. And a 0 is the hot path is being run, versus the 1, 0 is the hot path is not being run, 1 is your hot path is being run, like the main loop that's always looping. And think of the grand scale of that, all the zeros and ones. How many are them? How many are 0? How many are 1? So it's mostly 1, right? Most of the time your code is running, it's running that little loop that's happening. So if you can optimize that, that might be your biggest gain, right? Another way of thinking about it is thinking of entropy. Take those zeros and ones and use a WinZip on it. How well is it zipped? Because if it zips together like 90%, that means that it's 90% ones or the same information. So it's always the same thing happening. So think of it that way. If your code is a mix of things happening, okay, yeah, sure. Think of what you can optimize. But most of it is that loop, so, yeah. Especially in games. Because in games, yeah, you have objects. You need to do something to the object. You need to take the state and then build the commands to draw it and then send the command out. Take the objects, update the objects, build the commands, send them out, right? You're doing always the same thing. Is that big O of what? Like, no. It's O of n going through the objects, O of n building the commands, send them out. Right? You might do some like pathfinding. Okay. Because in the update of the state of the objects, you might do some pathfinding. And that might be like, okay, you need to think about, am I using A star? Am I using GNOME optimizations, right? What am I using? So there you might think about it, but generally no. Okay? Good. So who am I? Nobody cares. So a good way to describe this talk is a bit of silly fun. Some real-life use cases. This is for like a general audience, so you might think about this kind of stuff, but yeah. Yeah, this might apply to you as well. I've done a previous talk. This is like from a couple of years ago. That was way more serious than this talk. And it was about how humans learn information and how humans remember things. And in that talk I said, unfortunately, in this case, there's considerable evidence in many situations that this strategy, the 1-hour lecture, is rather poor. In 1971, they found that lectures like this, to learn things, is not good. 71, think about that, and we're still doing it. A lecture may inspire, it might motivate, it might inform, but it rarely fulfills the principle for effective learning. It is certainly inadequate for developing high-level skills. What are we doing? Right? What are we doing? We've known this since the 70s. Yeah. So, I cannot in good conscience make a talk after I found that out, trying to teach you something, right? So instead, I made a silly talk, which is this talk. So, warning, I will do stuff to video games in this talk. If you're going to do similar stuff to video games, I'm asking nicely, only do this to single-player, non-online games. Okay? Pinky promise? Yes? Thank you. It's not something crazy, but I feel I need to add this warning. So, playing games is great, but I'm also a programmer. How can I add these two things together? Well, you can make games, which is what I did. Okay, but now what? Because games are just applications. So what can we do to control those applications remotely? What are the different challenges you'll face when trying to interact with complex software? And can this be applied to interacting with other software? So, because we're talking about games, we have to have game terminology. This is level 1. What if the game I would like to play programmatically, which is what I want to do, supports playing it programmatically right out the box. What game do you think that is? Yeah?
Something that goes in sequence or programming game?
Yeah, programming games.
Would programmatically mean that the way you interact with the game is coded?
I can code, and I can take the output of the code, which can be some bytes or whatever. I can give those to the game, and the game runs it. Doom. Yes, Doom supports playing it programmatically. Kinda, but yeah. So, who's played Doom? Anybody? Yeah, there we go. I don't need to explain Doom. Doom is a 1993 first-person shooter, and it also kind of redefined a few aspects about video games. The look and feel, online multiplayer, game modification, and video game speedrunning. Who here watches speedrunning? Yeah, good crowd. I like this crowd. When I do this at like normal conferences, there's like 2 people. So I cannot go over everything, but I'm going to look at the last one. Because whenever there's a timer, people try to be the best. People try to be the fastest. That's just human psychology. And Doom is no exception. So anytime you finish a level, you'll get this. How many kills, how many items, how many secrets, and the time it took you to beat the level, and the time from the developer. And I love this screenshot because they finished the level by finding all the items and all the secrets but killing nothing. Yeah, that's a good one. So here it took 1 minute and 16 seconds, and the developer took 2 minutes and 45. Cool. And people are still trying. To this day, they are still trying to make Doom go faster. So the first level is finished in 8 seconds in 2019. And you can see those files. There's files over there, e1m1p897.zip. And what is that file, right? It can't be a video file because the game came out in 1993. So, if you download these files, you notice that they're actually pretty small, a few kilobytes. They're called demo files, .lmp for lump, but they're usually called demo files. And they contain what input the player pressed every single frame of the game. So here's the header of the file, you have the version of the game, what the expansion pack and other flags that might affect the thing. And then for every frame, every line of that file is, are you pressing forwards or backwards, are you strafing, are you turning, and any interactions you're doing. Every file, every line, go again and again and again. And then, if I record my playthrough, and then I give it to you, you play it, what you're actually just playing is you're doing the inputs. Again, my inputs. So there's a tool called XDRE, and here are the lines. Moving forward, strafing, etc. Turning left, and I can then play out the game. You can see if I back up, you can see all the values changing, direction, position, that kind of thing. It's kind of cool. So this is possible because Doom is deterministic. Doom is a single-threaded application where every single entity on the map patiently waits their turn, always in the same order. Some more code. Here's some actual Doom source code if you want to read. Game source code is weird. It's very weird to look at. And when they want to do something random, they just pick a number from this list. So if I want to do something random, I get the first number, 0, cool, and I do whatever that is. Some enemy wants to do something random, they get the next number, 8, they do something with that. Everything in the system is using this list, and they're always using this index. It's a single-threaded application, and the randomness is the same. So if I press forward on this frame, and I press shoot on the next frame, I will pick a number, 109, and that will be the damage I did, whatever that means. But if I press shoot on the frame after, I might get a different random number. This is why the frame by frame matters. So then there's an index that's incremented, and the next entity will get the random number. And the entity doesn't just mean like enemies. It can be like the door making a sound, or if you shoot the wall, it will have like a little puff of smoke. How the puff of smoke looks is different. So, what if you wanted to take Doom and convert it to Cplusplus or some other language? So Doom is in C originally. So this was started by Jason Turner, Who knows Cplusplus Weekly on YouTube? Ooh, you need to watch Cplusplus Weekly. I recommend that. It's like bite-sized videos about one Cplusplus topic, like 5-10 minutes, talk about one thing, and he's an expert in that field. So it was started by Jason Turner to convert Doom to C++, and then continued with from Patricia Oz, and then I was dragged into that as well. So if you're taking a big code base like Doom, and you're changing things, and you're modifying things, how do you know that the changes you've made haven't broken the game? Because, okay, you could play the game, you could write some tests, but how do you know? How do you know? Well, we have the tool in our hands right now. So there's a thing called approval testing. It's a methodology where you focus on the output of the code that you're running, right? Think of it like a Git diff. So the program outputs something, you write the new version, you get the output, and you do the diff. Is the diff the same? Because if it's the same, then you're likely to have the same application. So this is useful when you want to do a complete rewrite, or if the original source isn't available. So you can run Doom demos, so they will run to completion, and you can ask it to give the stat output as a text file. So you'll get this little thing, E1M1, map1, took 51 seconds, killed 5 out of 6 enemies, found this many items, found this many secrets. So the demo played the game, and this was the result. If I then go and change the game, refactor it, change the function, something, right? And I run it again, I get the same results, I'm more safe in knowing that it's okay, right? And then if I have a lot of these, I'd feel better about the changes that I made. So if I play this demo on the new version, I should get the same results. Another tidbit, the game doesn't need to render on the screen, because as you know, rendering is just the visualization of the state. So we can add a flag to the game where we just don't run the graphics. We don't even need the graphics card. We run the game in the command line. This also means that I can run the game as fast as possible, because we just need the demo to run through. Because the game is a deterministic system, it's always going to give us the same results. I can just run it as fast as possible. So even if it's a 6-minute demo, it's going to run immediately. So, putting one and one together, we can play the game using a known good version, collect a bunch of stat outputs, save those stat outputs into a folder with all the diffs, run the game with all the flags, get the output, do a diff of the output, which means that I can run Doom and Github Actions. So here is a build of the game running on Ubuntu, Windows 64, Mac OS 11, Windows 32-bit. And I have all of the builds. The demo check is here. Took 0 seconds because it's immediate. It passed. Everything is okay. Here's how it looks. For those who play Doom, you get like the Doom shareware. Yep, and then all green. Then I can go again. I can do more changes, do the build, see if everything's okay, do more changes, do the build. Right? Cool? Yeah. One more? 2 more. Yes?
What do you say, make more changes?
Converting it to C++, because it's in C. So a lot of pointers, a lot of manual memory management. Sorry. Oh. So, what's more? More games. Level 2. What if the game you want to play doesn't have the support that Doom does? Bejeweled. Who's played Bejeweled? Who's played Candy Crush? That's kind of the same game, yeah? So, Bejeweled is a match 3 game. You pick a gem, move it left, right, up, or down, and you can join them together. If you get a 3 of a kind, you get a bonus. You get a 4 of a kind, etc., etc. After the match has been made, those gems drop, they go away, and the board drops down. Simple enough, right? So, I would like to make an application that plays Bejeweled 3 for me, automatically. Should we make that? Yeah. So, the plan of action is pretty simple. First, we need to figure out what gem is where. Then we need to pick a good move from that state of the board. We need to move that gem, and then repeat. Right? Who's ready? Yes. So it's a C++ project. You use C++, CMake, VC packets, and OpenCV. OpenCV is used to grab the screen, and then I use some image analysis. OpenCV is a computer vision library. If you haven't used that, it's a very good one. Pretty old one, but it's pretty good. So, what gem is where? The game actually looks like this. If you're playing it, it's like low res, but I'll make the screens bigger for you. So, each gem is 64 by 64 pixels. We know that, that's the same. That means that, and the board is always the same size, and the board generally doesn't move, so it's always the same place. So it's a nice little static screen. That means that at 261 pixels and 37 pixels, that's where the board starts. So I can offset from there to try to detect what gem is where. From that information, I know where each cell is. I might not know what gem it is, but I know where in the picture it is, actual pixels. But how do I know that this is a green gem? So, any solutions? Yeah?
If you know like the RGB value of a pixel
Yeah.
within the space, you can just check for that pixel relative to the space every time to check for a gem.
That's exactly what I did. Let's take the center pixel of the gem and check the RGB colors. Yeah? There's a problem with that. If you click the gem, it spins. So the center value changes. Damn, doesn't work. Yeah?
You can check for it only once.
Check it for only once, yeah? So you like have the state. There's another problem in that is when things move and are like resolving, you don't know when they're done. Because if you match at the bottom versus matching at the top, it takes longer to match at the bottom. So you have to like wait and sit. But yeah, you could. So, since I'm using OpenCV to do the pixel detection and that kind of stuff, let's use, it's a computer vision library. They have a thing called template matching. So you can give it a template, a photo, and then you say where in another photo is this template. That seems to be exactly the thing, right? So here I have a photo of Messi playing some football. And then where in the bigger picture is Messi's face? So where the brightest white is, that's where the picture is. So Messi is here, or Messi is here. And since this is statistics, like where the other values are, it's less likely where Messi is, right? So you pick the highest one and that's the center, right? Seems perfect, right? Because we have these shapes, we have these colors. Like this is unique for us, so this should be great. So I have a board, and I have the matching. Who can see the problem? Yep. Oh. Ah. Yeah, so I kept it open, and the game was giving me a hint. It's like, hey, if you move the yellow one, that should be good. So it gave us like a little arrow around the yellow to be like, hey, you should move this one, which changed the template for the red one above it. So that doesn't work, but we have this threshold I can adjust. How aggressive do you want to be at finding it? So then, if I change the threshold, I play the game a little bit more, it thinks this orange one, which is like glowing special whatever, it thinks that one is the red one. And no matter what kind of threshold adjustment and changes I did, I never found any good ones. And then I was trying to like figure out like why. Like this should be easy. Like they're so separate from each other. The issue is, a lot of these algorithms make the templates black and white, which is our main advantage. Our main advantage is that there's colors. The shapes are, some of them are different, but some are like kind of similar, right? So that's kind of ruins the whole thing for us. That's why these things are happening. So let's go back to the idea of color, or to the idea of hue. Instead of RGB, we can use hue, saturation, and value. So hue, for those who don't know, is basically where on the color wheel you're pointing to, right? Are you in the greenish area? Are you in the purplish area, right? So, and then also I grab a 32 by 32 center area of the gem, and I ask OpenCV for the average color of that area. So when I click it, it's turning, but the average color isn't changing that much, and it's still pointing in the greenish area, right? So I check against where it's pointing. I also use the RGB to help like differentiate, but yeah. So I went through and I played the game and I checked, I printed out the hue, saturation, and value for all the gems in all the situations. Under all conditions, they're like on fire and glowing and whatever, yeah? And I have a chart of where their minimum hue is and their maximum hue is for every color. We have the blue, orange, red, green, etc. And you see, for example, the green one is really separate from all the others. The orange and the yellow kind of overlap, but they should be okay. The blue one is kind of safe, but the red and the purple kind of overlap sometimes. But we can use the RGB to help us there as well, to disambiguate. So I made a really complicated function that takes in the hue, saturation, and value, the average color, and I ask, if the hue is over 85 and less than 115, then you are blue. If the hue is yada yada. I've trimmed the function a little bit, but this is generally what it is. Because then I can disambiguate. If you're here, I know you're red. If you're here, I know you're orange. And this works, even if you click the thing. Cool? That was one. Where's number two? Yeah?
How do you account for power-ups that change the color of the gem?
You can actually see that in a bit, because it does move, but making a fail move only takes like a half a second, so then it can, if it's like moving or messing up.
Yeah, but before there was a problem that it's perhaps assumed that jewel, the power-up, is another type of jewel. So how do you still indicate that the jewel with the power-up is the exact same?
So when I was doing the, like there's a thing I didn't show in the chart, that I know that purple 146, 149 is purple, but purple shiny from 121 to 144 is also shiny. So it's like I'm taking slices out. I know that for a fact that if you're like this, you're either purple, purple shiny, which might not be all purple shiny. Purple shiny hue might be other values, but then I start, after I do purple there, I might do red and red fire, and then I do the rest of purple shiny, because I know red is like this, so I slice it out like that, so that works. There's a couple of cases where it's like, it's not sure, and there's some cases where it like loops around, because it thinks it's two colors, but it's good enough. But yeah, I get the values. So, pick a good move. What does it mean to be a good move? And again, initially I was thinking like cool algorithm, deep learning, min-max, something cool like that. But after the whole color fiasco, I thought like, hey, let's try something simple. Wow, very dry air. Let's try something simple. There we go. And it actually was. So I just started playing the game, which is a great excuse to start just playing the game. And I played the game for a couple of hours. And I had an idea. I still haven't recommended it. It's good. There aren't actually that many moves. Like, if you think of move as in like, this is the setup. Like, there are gems of a color here. There's another gem of the same color somewhere else. And I want to move it in a direction. Like, the colors can change, but the action itself, there aren't that many. So, can we just map them out? So I made the system where you have A, B, C. And there's an X, which is the thing we don't want. So I want to move C towards AB, so we have ABC. So in this case, the yellow one is in the way. I want to move the C over, right? So I make a vector, a pattern. So I have AB, so everything, the origin is A, then B is X minus 1, C is X minus 3. It's a horizontal 3i, and the solution is what is the vector operation I want to do. So I want to plus 1 to the 3, so the 3 is minus 2. So that means I need to move in that direction. I give it an ID and I give it a value. The value is then used if I have a bunch of solutions, because when you look at the whole board, you might get more than one solution. I want to pick the high value one, so I can sort the list. And then I put it back onto the list. So here I'm using in place back wrong. Look at that. Nobody's perfect. And here's another one, more complicated. So I have A, B, and ED, and then C there in the corner. I want to move C in. So it's a corner 5, I have all the points, and the C is minus 1 in the X direction. And I give that a higher value, because if I detect this one, and also the other ones, I want to do this one. because this gives more points. And then here's the last one, and there's 32 of them, which aren't that many, and also a nice round number, right? So, which move should I pick? Because on the board, we might have many. Well, you have a high value move, so we're going to pick that one. But what if you have two moves that are same? Let's say the only ones we have here are these two, the green one and the purple one. Which one of these should I pick? Yep. Yeah, because when you move the lower one, it creates more incidental moves that might happen. Because once they drop down and settle, you might get more matches on the way down. Cool. Now it's time to move the gem. And this is the simplest one. There's a Windows SDK called mouse input. And I basically want a function that looks like this. I want to click somewhere, and I want to go somewhere else. Click and drag. Start an XY, end in XY. So, for fun, if you want a function that converts from absolute to screen coordinates, you have to write a function like this. I'm just showing it to you because I'm going to use it a few times, but I'm just converting coordinates. So, I get the position of where I should be, where I should click on. I click. I move. No, I move it there. I click. I get the position of where I want to go. I move it there. I release. That's the function. Go to the place, click the mouse button down, find out where I'm supposed to go there, release the mouse button. Simple. Again, this is like a COM interface, very common in Windows. Not very nice. So, who wants to see a demo? Yeah, demo. So I have the game here. I've now played for 17 hours. Play, new game. Good. Let's see if it works. Nope. Did not open the solution. Sorry. Is it in? No update. That's weird. Fun. Who didn't pray to the demigods? Always the case. Let me see. While I'm looking at this, any thoughts? Questions? All succeeded. Maybe I can just... Where is this?
Would you want to link the program to start the game?
No, I had it already built, so... That was the thing. Let's see, Bejeweled. Boo, boo, boo. Out, I think. Build. Debug. Is it there? Yeah, Bejeweled. There it is. See, so sometimes it does this. It's very fun. So to fix that, let it finish. That's another thing, if you're debugging stuff like this. Hey, got it. Okay, now it goes. Yeah, well, sometimes hit a loop like that. If you are debugging code like this, and you let it run, and it's code that takes over the mouse, you can't do anything. I can't move the mouse, because the mouse is being moved by Windows. So I have to wait. So you have to have like a kill switch or something to do that. One more time? There you go.
So you need to run it for every new level?
so I have it now for the demo mode is I only let it run like 100 times or something like that. Because otherwise it just, yeah. I think because, so for the last demo, I think I know why it's doing that. The thing is, it's too fast. That's the issue. And also, you can see that Bejeweled allows you to move two at once. Yeah, okay. Yeah, because last time I did the demo, someone asked in the audience, what happens if I don't, because there's another reveal, I make it sleep for like half a second, or like a few milliseconds, because it actually is too fast. It's too good at this. If I build it again, it's too good, kinda. Let me see, so again. There we go. Less confused. Less confused. Good. Because yeah, if you look at the result, it's technically correct. Yeah. Yeah, not always perfect, but good. Yeah.
Shouldn't it prioritize the moves that are lower on the list?
It should.
So why exactly does it flips in the row rather than in a line?
Is there a move? Yeah, there's a move there.
Horizontally, and it should probably prioritize
Yeah.
matching horizontally
Yeah.
above everything that happens on the top of it.
It should have picked this one, the green one.
Yeah.
Yeah.
So why exactly is this happening?
I'm not sure. So, yeah, I had to do it quickly because otherwise it takes the mouse over. But yeah, good. All right. So again, you see, it's perfect. It's awesome. It's the best. But yeah. Okay, last level, level 3. Who's ready? Yes, yes. Yeah. What if the game has none of this? Yeah. It's not a simple game. It's not a simple state. It's not a board you can look at. So V, who's played this? Yeah. You're probably the audience that has most hands up that I've ever done for this demo. Usually like one person like, yeah, I've heard about it. Yeah?
I think I've seen this game.
Huh?
I think I've seen this game.
Yeah, it's a good game. You should play it. So it's called VVVVVV. I'll just call it V for now because, yeah. So for those who haven't seen it, it's a platformer game with the gimmick of you don't jump, you flip the gravity. That's the kind of the idea. There's kind of a little demo GIF. So you can, there's like temporary platforms. You flip the, of course, spike bad. Spike always bad. And you collect these shinies, and you also have to save your crewmates in space. And yeah, fun game. So V does not have built-in support for giving the game inputs. It does not have a simple game state in that sense, because we're moving between levels and then like get to color detection and that kind of stuff. And it's actually pretty fast-paced, and you need to be pretty accurate. Not like the Bejeweled demo where you can go in a loop forever, right? So the idea, right, was to be Hackerman, was to do some cool hacking stuff. What ended up happening is I was more this guy, right? So you kind of know this. You know the game loop, games applications, you get the user input. Again, this is a talk for general audience, so there's a few caveats with the game loop. Getting the input from the user, there might be no input. When you update the state, updating the state can take a long time. It also can be multi-threaded, and when you're drawing, they can also be multi-threaded. So, you know this, right? Who doesn't know this? Good, they taught you well. Good, this doesn't take time. It depends, it depends. Yeah, you have 16 milliseconds if you want to have a 60 FPS game. This, one of the ways to do it is this at least once every 60 milliseconds if you want to have a game state updating every 60 frames. And then you can draw as often as you can. That's one way to do it. You can also do VSync and all these kinds of other things. And an example, you don't have to go through this. You have a loop, you have a timer. I can process the input, and if I owe time, so if I'm in debt, if I haven't updated the game state in the past 16 milliseconds, that means I owe time. I can update the game state and decrement how much I owe, and then I try to draw as often as I can. So this is just one way to do it. So that means that your game state always updates at a fixed pace, and when you draw as often as you can. You can also have dynamic here, but this then, the issue here is that it depends on the computer, how fast the computer is, and you don't want that. Good. So, V actually has a few advantages, and why I picked the game for this project. It's open source, so you can go and check if you want to look at the code for it. This is part of the game loop, if you want to look at that. That volatile always annoys me, but it's there. It's very strange volatile. They also have a delay for sleep. It's single-threaded as well, which makes the project a bit easier to work with. And it has a bunch of customization options. There's like an advanced options here. And if I toggle it to 30 FPS, in 30 FPS, the game runs a input check for the keyboard input for the user. It runs a game state update, and then it runs a draw. Then it does one input check, one update, one draw, always. Which is really beneficial for what we want to do. So, here's my plan. Launch the game as a paused child process of some loader. So the memory of the game is inside the loader, so the loader owns the memory. And then inject a DLL into the game process. Hook the function that creates a DirectX device in the game, get the address of that device, intercept the game's draw call to call our draw call first, and then before each frame, we send our keyboard inputs. Sounds fun? We game? Hackerman? Yeah. So, in the loop, I'm hooking here in the draw call. So I intercept the game's draw call function to send keyboard inputs to Windows. We could hook here. We could hook in the processing of the input. But we actually want to draw some nice debug UI. So it's good to be in the draw section because we have the actual rendering device. So we can put our debug UI on top of the game, which is really nice. So, some of you might think, wait, that's illegal. I really like how high def this image is. Because this is a meme from like 2006 or 5 or something. This is from Red vs. Blue, yeah. And like, Red vs. Blue was never this high def back in the day. So someone remade this, yeah. But yeah, this is illegal. Windows will say, operation did not complete successfully because the file contains a virus. Yes, I cannot run this. Even in the command line. Here's the thing. I cannot run this in release mode. I can run this in debug mode. It only works in debug mode. Apparently, another hooking tool that you can use works in release mode, but the one I have for the demo only works in debug. So you will see the debug version, but that's fine. But yeah, when you are working with this kind of stuff, and if you're Googling for this kind of stuff, most of the help and most of the people who are helping you with this kind of problems you have are cheating forums, like Counter-Strike aimbot forums and that kind of stuff. So yeah. I use detours from Microsoft. That's a library to help you basically rewrite the functions to where they go. For those who haven't done this kind of stuff, the idea is that you have a function that you would like to call. Someone else has a function. The idea is that you will get the memory address of their function, and you store that memory address. You basically rewrite where that memory address should point to, that function memory address, pointing to your function. You can do stuff here. You call their function. You can do stuff here, and then you return the original value. So it's a detour. So your function is called. You still do the work that was originally asked off from the function. So it looks like the function was called, but your function was called. You did some other stuff, and then you called the function. So it's called a detour. For those who haven't worked with DLLs, if you make a DLL, you don't have a main, you have a DLL main. And the reason why there's a different main is that the DLL main can be called multiple times. And you have the reason of why it's being called. So you can initialize some values. I can initialize the detours library. The reason could be when you're being attached. So the DLL is being attached to a process. I can do some work. I can call and rewrite their function. And when I'm being detached, I can put the function back to make it look like I wasn't there. So yeah. And like with any research and any kind of stuff like this, you of course go and see, has anybody done this? And a lot of people have done this. But I found this project by Tom Gascoigne from many years ago, 12 years ago, where they were basically only overloading the draw call in this library. And this was the basis for a lot of code that I had. And it says, whoops, forgot to commit a new class at the top. Yeah, I know that feeling. So thank you, Tom. So I have a class called hook process. When that starts, I will get the name of the DLL that I would like to inject, and the mode of the process that I would like to start. And I started suspended. And if a process is started suspended, it's there, the memory is there, but it's not allowed to execute yet. So it just sits there. I create the process with those commands, and I inject the DLL. So detour create process with DLL. Again, why I use the library, because it's just a one-line call. I then resume the game can call, and then I wait for the game to exit, and then I can have some helpful output. So this is the loader. That's kind of the only thing it does. Starts the game paused, injects a DLL. The DLL gets to run, gets to do its thing. Once the DLL has done its thing, the game is resumed. So the game can continue. So, what is the DLL? So when I'm being attached to the game, I call hook create device. Just a function called hook create device. And if you're doing this kind of stuff, message box is a really helpful thing. Because sometimes you can't debug. Sometimes you can't put debug flags or because it's another process being run. So, and it's also kind of tricky to do printf because the DLL is doing the printf, like where is that going to come out? So you can do message box, pop up a message box so you can know when things are happening. And I don't do anything for the details because I don't care. So when that runs, I can get a message box that says hello hook. So I'm now hooked into the game. So when the game starts, it wants to create a DirectX device. And once the game has created their DirectX device, they'll use it to draw stuff to the screen. So I want them to create my DirectX device. So when I start, I create a DirectX device just to get where it is in memory. So I will get actually the virtual function table of the DirectX device, which is that nice dereference there. And then I release the device. Because I just need to know where in memory the DirectX device is. Because I want to rewrite where the functions are. So I know who has played with virtual function tables? Yeah? So if you have a class, there is basically like a dynamic class that can have different, basically different functions based on, different functions and different functions where you call it. In the beginning of the class, they have a virtual function table, which is where the function is in memory. Because the function isn't on the class, the function is somewhere else. So this is, the virtual function table is in the beginning of the class. And I know at offset 16 bytes and offset 42 bytes, that's where the create device and end scene functions are. So I can change them. So I store the original create device, which is somewhere in that memory, and I say that my create device is there instead. So the memory that had the create device object now points to my function. So when the game wants to create a device, they call my function. So we spawned the game, we attach the DLL, sorry, we hook the create device, and now when the game calls create device, they call our function, and then we need to rewrite the end scene function because we need to create the device first before we can overwrite the end scene function. So this is the create device function. I actually just call the original create device function because I want the device to be created, so I want to be nice. Some error handling. I rewrite back the create device, so if anybody else is creating a device, that's okay. And then I overwrite, I get the virtual function table again. I store the original end scene, and I overwrite the end scene with mine. So now on this specific device that the game created, I have my end scene function. So game is running and game rendering hooked. So now every time the game wants to render something on the screen, my function is called first. So, to wrap it up, not much left. What time is it? Yeah. Here's my endScene function. It just gets a device. I call the original endScene function, and I can count frames. I can have a variable that counts the frames, and then I can say on frame 1, so we have the same Windows API thing like before, but instead of mouse, we have the keyboard now. I press the spacebar. And on frame 2, I release the spacebar. And this works. So I can exactly, frame by frame, tell the game to do specific things. Which means I can create a very complicated format. So I read some data from a file. I have data like this. So big S means I press the S button on the keyboard. Little s, I release the S button from the keyboard, right? So on frame 2, I press S. On frame 3, I release S. On frame 8, I press D. On frame 9, I release D, right? And these frames, I don't do anything. And then, for each one of them, I press those actions. I do those actions. So that means I can play V frame by frame. Wants to see demo? 2 people, okay. Yay! So, I have the loader. Oh, we have sound. Again. Yes, which means if I can slow the game down. Because what if I put a sleep function in the draw call? So you can see in the corner, I'm on frame whatever. This is how many milliseconds the frame is. And I can slow it down even further, 1 frame at a time. This is how I built the file to play it. Because I know that on frame 216, I should do something, right? I had a question in the back. I had a hand somewhere, yeah?
So is this the process of how you do tool-assisted speedruns?
Yes.
So you have to start from scratch and figure everything out in every game?
Yeah.
Okay, so there's no general tools that...
No, not that I know of. And a lot of these, I talk a bit about it a bit later, a lot of these use emulators, and in the emulator they can do the step-by-step, frame-by-frame thing. So the emulator supports it, but this game isn't running on an emulator, so I can't do that.
But you could make machine learning out of it, right? Like technically.
We could, yeah. Because the output file is just an output file. And I can also run the game as fast as I want. Because it's, again, deterministic. So here's the one that gets a trinket. So, I love this one. Yeah, because, so you're in game development. I'm guessing you've heard of coyote time, right? When you leave a platform, you can still jump a frame or 2 after you left the platform. So here we are, and, oh, okay, pretty close. Up, not good enough, and then, no, it's okay. And then I love this one, the last one, because so the game allows you 2 frames after you left the platform to still jump, which is pretty good. And this is for the people who have played the game. There's a challenge in the game called VVVVVV, which is because you can't jump, you need to flip the gravity. That means that you're like on the behest of whatever is above you. But what if above you is a big gauntlet of spikes that you have to go all the way up top and then all the way back down just to get over a little box, because you have and all the way back down. And then just because this one box is there, because you can't jump over it. One more time. and then, boop. Yeah, good. Cool. So, let me see. Yeah. It's a bit of thing at the end. Yeah. Games are neat. It's fun to play with them. This is a silly thing. When you have an application and you don't have the source code, there's always a way to interact with it automatically. AKA, you can still test. So this has been a talk about tests. You should write more tests, because you can. For those curious, testvideos.org for tool-assisted speedruns. For those who are interested in that kind of stuff. They have a lot of emulators in place and games you can play with. For people who are interested in Doom, there's a DSD archive, Doom Speed Demos archive. A lot of the edge cases for Doom I actually got from them, like demons infighting and that kind of quirky thing. So if you're curious about that, DSD archive. There's also the classic Doom archive, if you want to look at that kind of stuff. The code is all on GitHub, if you want to look at it. So my GitHub, VVV hook, my GitHub, Bejeweled player, and the Doom is on Patricia's GitHub. Yep.
If it's not deterministic and it doesn't give you like your Bejeweled, it's not deterministic.
No.
But it's not like it's very challenging. But let's say I have a challenging game like I don't know, I saw Smash Bros. Let's say there's a dimensional in Smash Bros. And it's non-deterministic. Then you can make a task which could be one set of RNG. But if you ran it multiple times, it would sometimes not work.
Yeah, level 4. Then there you go. Should get you going. Because these are good questions, because you're like, wait, what if, like, so yeah, good to be curious. And it's my face again. There you go. Thank you. I need 5 questions. No, 10 questions. No. Any questions? That means you're experts. You know all this. Good. Yeah?
I have one question regarding the example you showed with parallel, doing the fetching and execution in parallel. Is that roughly what a thread is?
Yeah. So, and also there's talks of like, that you have a CPU and they have many cores, and cores can also have threads. It's just the idea that like there's a thread of execution that is happening. So if you make a thread, there's always never a guarantee like where it's run. It's just the idea that it's being run somewhere, right? Sometimes when you make multi-threaded applications, it's nice that you're always on the same thread, but sometimes also you don't care. You just need your data to be running somewhere, right? Yeah.
What is meant with like the L1 and L2 cache being inside the core?
Let's see if I can get a not cache size. They're actually in the CPU.
Okay, so it's like placed on it?
It's in the circuitry. Yeah, part of the circuitry is the cache. So they're actually